Okay, for what we have in the next portion, still on the same section as substitution methods, we have what will be regarded as exact differential equations. And for what we have in this particular setup, okay, so if you notice we have some partial differential notations, and now for what we have here, now we have a first order differential equation, okay, where we have okay, of the form where we had the function of x and y with respect to x is equal to a constant. And now for this particular identity, okay, if we were to write in expanded form using partial derivative notation, okay, so we have partial derivative of the function with respect to x plus df over dy, and the partial derivative times the partial in y dx is equal to 0. And now we have just in the rewrite, and I'll get into some of the specific cases, but where we have the variable m, okay, this will be where we have the partial derivative in x of x and y, and let n be the partial derivative in y of the function of x and y. And here we have m plus n dy over dx is equal to 0. And another way that you could write this is that if you were to multiply this equation by dx, you have m of x and y dx plus n of x and y dy is equal to 0. And this equation will be regarded as exact, okay, if we have the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And now, just to give you a bit of an example of an exact differential equation, so I'm just going to try to map these two items together. And you notice we had 2x plus 3y plus the quantity of 3x plus 2y dy over dx is equal to 0. And now just notice we had this format here. So we got for 2x plus 3y, okay, so that is going to be your m of x and y. And we have for 3x plus 2y, that is going to be the n of x and y. And displaying what we have here in this particular format. Okay, so we got it in this particular format. Okay, and now we're looking at seeing if this equation is going to be exact. Okay, so just taking what we have here. Okay, so you have for the partial derivative of m with respect to y. So we're looking at taking the partial derivative with respect to y of that which represents m in this case, which is going to be 2x plus 3y. And for the partial derivative in y of 2x, that is negligible. That of 3y is equal to 3. Now, for the partial derivative of n with respect to x, so we're looking at partial derivative d over dx of n, which I have at 3x plus 2y, and that of 2y is negligible. But now for the partial derivative in x of 3x, that is equal to 3. And since we have the partial derivatives equal to each other, well, these equations are going to be exact. And so we have with these functions being exact, so now we can set things up whereupon we can say that we have f of x and y is equal to the integral, where I have m of x and y dx plus g of y Okay, so for the integral, okay, that we have of m of x and y dx. So I'm integrating with respect to x of okay, so I have the integral of 2x plus 3y dx, and so that is equal to x squared plus 3xy. Okay, and so for what I have here, so we have x squared plus 3xy plus g of y. Okay, now for following through, so if I'm taking the partial derivative of our function f with respect to y, okay, I want this to be equal to n of x and y. Now looking at what we have with the statement. So we're taking the partial derivative with respect to y of the quantity of x squared plus 3xy plus g of y. So that of x squared goes to 0, that of 3xy goes to 3x. And we have plus g prime y. Okay, and I want this to be equal to n of x and y. So n of x and y, we have a 3x plus 2y and if you notice, okay, we have same terms of 3x and g prime y is equal to 2y, and so g prime y, okay, we have the derivative of g with respect to y, and separating, okay, so you have dg is equal to 2y dy equal to y squared plus a constant. So we'll say we have y squared plus c of 1. Okay, and going back to our function f of x and y, that is going to be equal to x squared plus 3xy, then you have plus g of y, so by then we have y squared plus the first constant, and you have what we regarded as the constants being absorbed, and okay, so if I isolate the constant, we have c is equal to x squared plus 3xy plus, and I will mention I'm going to have this on a separate page, okay, and I'll have this within the notes for the week, but the example we just dealt with is a case of a homogeneous equation, and I'll show you the approach, like going back to the v substitution. And I think that taking the approach of using the partial derivatives, you will likely find is a more friendly approach. So I'm just going to have as a written set of results, okay, the approach taken with v substitution. So I would just have that. I'm not going to record that portion, but I will have that as a document. And so let me give you something that might be that which has a ring of familiarity to it, and just kind of maintaining exact equations. But let me kind of give you a reference point, something you can go by. When we looked at first order linear, differential equations. Like if you were to take this and let's say put the leading term along the lines of dy over dx. So if I were to divide the equation by x squared, and going back to what we have with integrating factor, so you have like your p of x is equal to 2 over x, and for the integrating factor you have like e to the integral p of x dx, so that is equal to e to the integral of 2 over x dx. So you have e to the 2 times the natural logarithm of x, or e to the natural logarithm of x squared, and this is equal to x squared itself. And if you notice, okay, if we multiply the standard form by x squared, and 0 times x squared, well, that is going to be at 0. And if I were to distribute, well, guess what? I would go back to right where I started from. But notice we have on the left-hand side, we have what will otherwise be the product rule expansion of multiplying, or taking the derivative in x and multiplying the integrating factor x squared by the independent variable y, and freeing up, so we have x squared y is equal to the integral of 0 dx, okay, which is going to be a constant. And so for what we're going to have ultimately, once we multiply by x squared, you can see we have y is equal to c over x squared, or c times x to the negative 2. Now, so this is what we have when we took the first order linear differential equation treatment. But now let's say that in terms of an exact differential equation, so you have switching the terms around. Let's say if I had 2xy plus x squared dy over dx is equal to 0, and again just multiplying by dx, so I have 2xy dx plus x squared dy is equal to 0. So we have just in the framework, okay, so your m of x and y is equal to 2xy, and for the n of x and y, well, that is x squared. And looking at taking the partial derivatives, okay, so for partial derivative of m with respect to y, so okay, at taking the partial derivative with respect to y of 2xy, so this will go to 2x, and then taking the partial derivative of n with respect to x, and that is equal to 2x, okay, and so in this case you have 2x is equal to 2x, and so this differential equation is exact. Now, and let's say that just for the follow through, okay, so you have for the function of x and y, again we're looking at the integral of m of x and y dx, and again we have followed by g of y. And for the integral of m of x and y, so you have m of x and y is equal to 2xy dx. And here we have the integral. Okay, so m of x and y is equal to 2xy. And we have dx. And so this is equal to x squared times y. And looking at what we have, again, so the integral, we have x squared times y. So we got the function of x and y is equal to x squared y plus g of y and again we have the partial derivative of this function f with respect to y is equal to n of x and y. So looking at taking the partial derivative with respect to y of our function f so the partial derivative with respect to y, so you have that of x squared y plus g of y. Okay, so this will come out to x squared plus g prime y, and again, so we have is equal to n of x and y. So we have x squared plus g prime y. Then we have, okay, so just taking what we have now. Okay, so we have is equal to x squared. And if you notice, we have identical terms on both sides. So right away, we're going to have that g prime y is equal to 0. And again, just for g, okay, that is going to be equal to a constant. For once you separate dg and dy, we got dg is equal to 0 dy. And the antiderivative again. So you have g with respect to y is going to be equal to a constant. And going back to what we have with our function. So we're going to have that f of x and y is equal to x squared y plus c of 1, and letting the constant be absorbed, so we have that c is equal to x squared y. And if you notice, when we took the first order linear differential equation approach, we have y is equal to c over x squared. And if you notice, if I multiply by x squared, guess what? We come out to the very same thing. So we have that c is equal to x squared y. And in fact, with both versions solving for y, we had that y is equal to c over x squared, or c times x to the negative 2.